In this video, we will be looking at exponential functions and their graphs, and then talking about a couple of application problems. In this section, what we're doing is actually taking the variable and the number that we're putting as an input, and we're switching them. What we've been talking about up until now, we would have a number such as 3, which would be listed as the exponent, but we would have the variable as the base. Or we would have x as the variable and 2 as the exponent. Now we're switching the order of those, and the variable is going to be the exponent, and the base is going to be a constant number that stays the same. Our base is always going to be a number that is greater than 0. And it's not going to be equal to 1, because if it were equal to 1, if we had 1 to the x power, that's not very interesting, because 1 squared versus 1 cubed, we're just getting the same number every time. So we're not going to have our base, or a, be equal to 1. Here are a couple of examples of exponential functions. In the first example, 2 is what we call the base. In the second one, 1/2 is the base, and in the third one we have 3.57. The base doesn't have to be a rational number. It can be an exponential number, or sorry, a decimal number, and it could also be a rational number, an irrational number. Here are two examples of exponential graphs. We hear the term that something is growing exponentially all the time in regular language, and what we mean by that is that something is growing very rapidly. And in fact, if we were to compare these graphs with, say, an x squared graph or an x cubed graph, they're growing at a rate that's actually faster than something that would be a regular polynomial. The graph on the left is a standard exponential where the base is a whole number, and we can see that on the right-hand side of the y-axis, the graph is growing in the way that we would consider to be exponential. But on the left-hand side, the graph is approaching the x-axis very, very rapidly. That's because when we get onto the left-hand side, we're taking numbers like 1/2 raised to, let's do it like this. We'll do 2 raised to the -1 power, or 2 raised to the -2 power, or 2 raised to the -3 power. When you have a negative exponent, that means that the number is in the wrong location. It should be in the reciprocal instead. So the number 2 to the -1 is the same as 1/2 to the first power. 2 to the -2 power is the same as 1/2 squared. 2 to the -3 power is the same as 1/2 cubed. So this is 1/2, 1/4, 1/8. As we move to different numbers in the direction of x, the overall fractions, or the y values, are getting smaller and smaller, and they're getting closer to the x-axis. So in this particular case, the x-axis is acting as an asymptote for this graph. Similarly, for the graph on the right, the x-axis is also acting as an asymptote, but in this case, we're looking at 1/2 to the x power, which is the same as 2 to the -x. Based on the math I was just doing there, we can think of 1/2 to the x as 1/2 is the same as 2 to the -1 power. When you have an exponent raised to an exponent, we multiply the exponents together, and that's 2 to the -x. If we think of the original function as f of x equals 2 to the x power, then when we have a negative sign up in the exponent, what we're saying is that we're putting a negative inside of the parentheses. When we put a number inside we know that negative signs are reflections, and inside the parentheses is always going to be left to right. right? And so that's why we're reflecting these two graphs over the y-axis, because of where the negative sign is. If the negative sign were in front of the entire function like this, that would reflect over the x-axis instead, and the graph would be down here. Wait, before I continue, the domain of both of these functions is going to be all real numbers, and the range is going to be from 0 to infinity, because we have that asymptote as the x-axis. Here are a handful of different functions. You can see the way that the patterns look for all exponential functions. For all exponential functions, they have the x-axis as an asymptote. So their range is going from 0 up to positive infinity, not including 0. And the domain is all real numbers. We can plug everything in. Of course, this is just for a standard graph. We could have a graph transformation where the graph is shifted up or shifted left, right, stretched, and then in that case, the domain and the range might change. One thing to notice about the graphs is that when we look at what the bases are, if we look at a number like, let's look at this one, 4 to the x versus 1.8 to the x. When we're on the right-hand side of the y-axis, the base that has a higher value is growing more quickly than the base with a lower value. But when I move over onto the other side, over onto the left-hand side of the y-axis, what ends up happening is that the number that has the higher base, which in this case would be 4 to the x, is actually going to get closer to the x-axis than the one with the smaller base. So it's going to grow more quickly on the right-hand side, but on the left-hand side, it's also going to get closer to the x-axis or get smaller more quickly. We have graph transformations just as we did with polynomials, where if something is inside the parentheses or within the exponent, then that's going to move the graph to the left and the right, where if it's on the outside of the parentheses, like this, where we have a 5 on the outside, that's going to shift up and down, right? Horizontal versus vertical. So in this particular graph, the whole graph is shifted to the right by 2 units. The way that this shows up is that all exponential graphs typically go through the point 0, 1. That's because any base that we have raised to the 0 power is going to be equal to 1. So input value of 0, output value of 1. In this particular graph, the whole graph got shifted over by 2 units to the right, so now that point got moved over here to be 2, 1. In the graph on the right-hand side, we have a couple of different things happening. The original graph was listed as this. Rearranging it or writing in a way that makes more sense to us, we changed the 0.5 to 1/2 instead. And 1/2 is the same as 2 to the negative 1 power. So here is the way that we're going to think about the graph. I'll rewrite this as negative 2 to the negative x plus 5. I'm going to move that 5 onto the outside. The negative that's in front of the whole function is a reflection across the x-axis. The negative that's up in the exponent is a reflection across the y-axis. And the 5 that's here on the outside is going to shift the whole graph up by 5 units. So looking at the final picture that we have here, I can see that the graph has been reflected across the x-axis. It's going down. It's also been, the normal graph would have been, because it's a 1/2, the normal graph would have looked like this, right? So it's been shifted, 2. If I have 2 to the x, 2 to the x would look like this. So we're reflecting it across the y to look like this, and then we're reflecting it down across the x to get this graph here. Now notice that the whole thing has been shifted up by 5 units, and so normally the asymptote is at the x-axis, but the asymptote has been shifted up to y equals 5 because everything gets shifted up, even the asymptote. The normal point of intersection, which is at 0, 1, also gets shifted up. It would have been shifted up to 0, 6, but then when it got reflected back across the new axis, which was created right here, that intersection point shows up here at 0, 4. So again, the normal intersection point is at 0, 1. We shift it up by 5 units to 0, 6, and then we reflect it across our new center point, our new asymptote, and the intersection point ends up at 0, 4. Here, the most common application is compounding of interest. This is the formula that we use for compounding interest, where A is the amount of money that's initially invested. So, A is the amount that we end up with, final amount. P is the principal, which is the amount invested. R is the interest rate, and the interest rate is always in a decimal number. So it'll often be listed as a percentage, and we want to change it to a decimal number. T is the number of times, and notice T is the amount of time in years. That's something that's important to remember. So T is time in years, and then N is the number of times compounded each year. So if it says monthly, then N would be equal to 12. It's how many times each year we do the compounding. In this example, we're starting with $100,000. That's our initial investment, so that'll be P, that'll be the principal. The investment is at a rate of 6.5%. Again, we change that to a decimal number, so that would be 0.065 is equal to R. And then compounded semi-annually, that's compounded twice a year. So that means that N is going to be 2. First, we're going to set up the function. And that would be the first part. This is part A. The first thing we want to do is set up the function that we can use to determine how much money we would have for a certain amount of years. So principal goes here. The interest rate goes here. We're compounding twice a year. And then this is 2n times t. We don't know what the time period is, but for part B, we're plugging in 0, 4, 8, and 10. And those are all reflected here. We're just taking the number of years that they're asking us and plugging it into the function. When we plug 0 in for time, that's just saying really no time has passed. Well, of course, the answer should be what our original investment was, and that's reflected here as $10,000. We can see the function graphed here on the right-hand side, and it matches up with the values that we're getting here. And again, these are all just sort of calculator problems. You could just plug into the calculator. When we talk about exponential functions, the number e comes up because it is a common application that's used in population growth. It's used in growth and decay, and it's also used in compounded interest that is happening on a continual basis, where the amount of interest is immediately reinvested, and then you continue compounding interest, including the amount that was just recorded, or the amount that was just made. The number e is kind of like the number pi in the sense that it is a rational number that has a decimal approximation. But when we look at the decimals moving out, there's no repetitions and there's no termination. So the number goes on endlessly. So it's considered to be an irrational number. That means it can't be rewritten as a fraction. Here are the graphs of e to the x and e to the negative x. They look similar to the graphs that we saw before because really we're just looking at, say, like 2.7 as the base. We can use the same sorts of graph transformations that we have in the past, where if we have e to the x plus 3, the whole graph will be shifted to the left by 3 units. What we're saying is if we had f of x equals e to the x as our original value, our original function, and then compare that to, let's say, f of x plus 3, where the 3 is going up into the exponent, because this is inside the parentheses, we're moving to the left. The second graph that we see here, I'll rewrite this. Let's rewrite this as f of x equals negative e to the negative 2x plus 1. So this is going to be a reflection across the x-axis. This is going to be a reflection across the y-axis. And this 2 that's sitting there is going to be a horizontal shrink. Remember that when we're inside the parentheses, in this case inside the exponent, that has the opposite effect of what we would think. So a number that's larger than 1 is actually going to end up being a shrink. And then the plus 1 is going to shift the whole graph up by 1. So the original graph, e to the x, would have been like this. We can see that we reflected it across the x-axis. Across the x-axis would have been here. Then reflecting across the y-axis would have been, so we had here, and then back over here would be across the y-axis, right? Back over here. And we're shifting up by 1. So normally we would have been at 0, 1 for our intersection. When we reflected down, it went down here to 0, negative 1, but it shifted up by 1, so that intersection point went up to 0, 0. Again, what I'm saying is the normal intersection point on the y-axis would be here at 0, 1. When we reflected down, it would have gone down here, but then shift the whole graph up by 1 because of the plus 1, and it would have ended up here at the origin, 0, 0. Again, you'll be using Desmos for most of your graphing, but it's just sort of an understanding of what's happening with the graph to understand how we're getting these end ultimate pictures.